What is up, my chemistry people? Free response time. Yes. The Bohr model of the atom was developed in the early part of the 20th century. A diagram of the Bohr model for one atom in the ground state of a specific element is shown below. The nucleus of this atom contains 9 protons and 10 neutrons. Part A. State the atomic number and the mass number of this element. Easy. Atomic number 9. 9 protons. Mass number 19. 9 plus 10. Again, read your question carefully here. All we're asked to do is state the atomic number and the mass number. No calculation required, no additional work. Answer the question, move on. Part B. Identify the element represented by this Bohr model. Well, how do we determine the identity of an element? It's based on the atomic number. Jump to my periodic table. Atomic number 9. Identity of element is fluorine. Boom! Part C. State the number of electrons in each shell of this atom in the ground state. Now, we're given a hint that there are 2 shells. But remember, your periodic table is a great tool when you're trying to determine the number of electrons and number of shells or energy levels that a given element has. Recall that each row represents a shell or energy level, and each box indicates the number of electrons in that main energy level. So in my first main energy level, I have 2 electrons. There are 2 electrons in the first shell or energy level. Back to the PT. My second energy level of fluorine, stop at fluorine, contains 1, 2, 3, 4, 5, 6, 7 electrons total. There are 7 electrons in the second shell. Boom! Moving right along in this problem. Part D. Using the Bohr model, describe the changes in electron energy and energy location when an atom changes from the ground state to the excited state. Okay, we need to describe both the change in energy and location for our electron. As an electron moves from the ground state to an excited state, it will absorb or increase in energy and move further from the nucleus. Boom! As an electron moves from the ground state to an excited state, it will absorb or increase in energy and move further from the nucleus. Boom! Again, one of those really important read carefully type questions. Have we described the change in electron energy? Yes, it's going to absorb or increase in energy. Have we described its change in location? Yes, further from the nucleus. So a question like this that's only 1 point, if you only describe the change in electron energy, but don't describe the change in electron location, you don't get any points. So read carefully, especially on a question like this where you're pretty confident and know the answer. Don't miss because you aren't reading carefully. Read it twice. Read it 3 times. Just read it. Part E. Answer the following questions related to the electron configuration of the element represented by this Bohr model. Subpart I. Write the complete orbital electron configuration for a neutral atom of this element in the ground state. Alright, I always like to use my periodic table when I'm writing electron configurations. Trying to get to my boy fluorine. I call him Fluor. Alright, start from the very beginning. Very good place to start. Orbital notation, we're in the first row, first period. We're in the first main energy level, the 1s. We can fit, boom, 2 electrons. 1, 2. Keep going. Now we're in the second main energy level, S-shaped sublevel. 1, 2. 1, 2. Keep it going. Still in the second main energy level, but now we've crossed over into the P sublevels. We can fit 1, 2, 3, 4, 5 electrons for ground state fluorine. Recall that there are 3 2p orbitals, and keep in mind Hund's rule as you fill equal energy orbitals, 1 in each, before you go back and put a second in each. Boom! Orbital configuration for fluorine in the ground state. Next, let's write the complete standard electron configuration for a neutral atom of this element in the ground state. We're just going to take our orbital notation, convert all those arrows to superscripts. Superstar. 1s2, 2s2, 2p5. 2 from the 1s, superscript 2. 2 from the 2s, superscript 2. 5 from the 2p, superscript 5. Subpart III. Write the noble gas configuration for a neutral atom of this element in the ground state. Back to the PT. Find the noble gas that comes before fluorine Helium. We put helium in brackets. This part of the fluorine configuration is the same as helium. So instead of writing that part of the configuration, we just sub in the symbol for the noble gas. Pick up right after that 2s2, 2p5. Boom! Noble gas configuration. Part F. Fantastic. In the boxes below, draw the Lewis valence electron dot structure for a neutral atom and most commonly formed ion of this element. All right, the Lewis valence electron dot structure. Our focus is on the valence electrons for fluorine. All right, now there are a bunch of different ways that you can do this. You've just written a bunch of electron configurations and you can use those, or simply go to your periodic table and recognize that fluorine is over here in group 7 and therefore will have 7 valence electrons. So my Lewis valence electron dot structure, I write the symbol for my element, fluorine, and I need to get my 7 valence electrons around this symbol. Starting at the right, gonna go counterclockwise until I get 7 valence electrons. Boom. That is my Lewis valence electron dot structure for my neutral atom of fluorine. Now, the most commonly formed ion. Fluorine as a nonmetal will most likely gain electrons to complete its octet. Notice that it's just missing 1 electrons for a complete valence level. So, for the most commonly formed ion, I'm going to rewrite my symbol F and then recognize that it's going to gain 1 electron. By gaining an electron, it's no longer neutrally charged. So we place our ion, the fluoride ion, in brackets and write that charge outside the brackets. Boom! Lewis valence electron dot structures. Subpart I. Identify one other neutral atom or ion that is isoelectronic with the most commonly formed ion of this element. Isoelectronic means same electron configuration. Now there are several different answers that you can put here, but we're only looking for one other. As you think about trying to answer this, go back to your periodic table. When fluorine completes its valence level to form the fluoride ion, it will have the exact same configuration as the noble gas neon. Again, we're only asked to identify, so I'm simply gonna write neon is isoelectronic with the fluoride ion. And as you think about questions like this, know that most atoms will try to gain or lose electrons so that they have a complete valence level, so that they have a configuration that is isoelectronic or the same as the noble gases. Everyone thinks the noble gases are so cool. Noble gases, I'm so noble, kingly, queenly. Ooh, I want to be just like them. Posers. And that is it. We are done with this free response.